Hello everyone, welcome to the second of these supplementary online sessions, supplementing the mechanics portion of Physics 1. We're going to be doing a bit more on vectors, so there's a few other things that you can do with vectors that we'll need in this course, so we're going to do them now. You'll also do these things again in Maths 1 if you're in first year at University of Leeds, but we're just doing them again here to really solidify the ideas and hammer home why they're important. So let's get started straight away. So last session, the other supplementary session on vectors, we did what vectors are, how to represent them, 3 different ways of representing them, how to use them to represent physical properties and scalars too, so that's really important. We remember that things like forces, torques, wave vectors, these things are vectors. Each component of that vector is a scalar, a size, and the vector part is a direction. And we represent different physical properties with each of these things. If we remember as well, scalars are the things that carry units, and vectors have an extra bit of direction. And we learned how to mathematically combine vectors and scalars using addition, subtraction, and a bit of multiplication. We're going to do a bit more of that today. So you should now be able to represent appropriate physical quantities using vectors in 3 different ways. So we've done force mostly and position in these supplementary sessions, but as you do the physics course in first year at University of Leeds, you'll start seeing vectors all over the place. But don't be scared, it's always the same underlying idea. A vector is just a thing with a size and a direction. We've learned how to perform a few fundamental operations using vectors, so that's addition, subtraction, multiplication, and we also did a bit of derivation, so we derived the formula for calculating the vector dot product. Interesting, but not 100% important for physics going forwards. But this session, we're going to learn what the vector cross product is. So we've done the dot product, we're going to learn what the cross product is, and we're going to learn the general use of scalars and vectors in physics. That's a typo straight away. So at the end of this session, you'll be able to use vectors to represent physical quantities in general and perform all basic vector operations that you'll need in first year physics. So that's addition, subtraction, multiplication, and division. So let's move straight in. More vector operations. What can we do? We've got this thing called the vector cross product. Now, if we remember, the idea, the concept behind the dot product was that we want something that's similar to scalar multiplication. So we want a way of timesing vectors together that puts them both into the same direction and then times their lengths together. So it's similar to scalar multiplication in that sense. But what we get out of the vector cross product, which is again an operation that we can just make up, it's a type of operation that takes 2 vectors and gives you another vector in return. So it's much more, how can I put it? It's much more complete vectors, right? We're not getting scalars out of this. One vector in, another vector in, and another vector out. So it's all vectors. How are we going to do that? Vectors in, vectors out. So let's think about it. Let's think about the history of this. Imagine we've just invented vectors, right? We've just invented them. We want something that's got a size and a direction, so we invent it, vector. We add an operation that's similar to scalar multiplication. So we've already invented the dot product, but now we want a new operation that results in a vector. What do? Just invent it, make it up, right? Maths, to me at least, is a tool, so we can just make stuff up. And this is exactly what Lagrange did in 1773. Just invented an operation that worked to do the calculations that he wanted to do. So I've just put a little note down here. It says some people... let's go back out of there. Oh, what's that bit at the bottom? How do I get rid of that? Never mind. Oh, there we go. Okay. So some people believe that maths is discovered rather than invented. That's a philosophy debate. I think it's invented. We make it up as a tool to do calculations that we want to do. But some people think it's discovered. That's philosophy. Talk about that in tutorials and things. But for all intents and purposes, Lagrange in 1773 invented the dot product, the cross product, because he needed it. He just invented it. So we're going to go through what he did. And we're going to use this diagram to do it. Oh, it says load the GeoGebra file. Okay. So I've got to load the GeoGebra file. So let's minimize this. Okay. So GeoGebra is just a free tool that you can get off the internet that allows you to graph mathematical things in general. It's pretty cool. So I'm going to load up a file that lets me describe what the cross product is. So the cross product is a way of taking two vectors and getting another vector. So imagine I've got a vector A here and a vector B here. They're not unit vectors, they're just vectors, any two vectors. Here in red we've got the x-axis, in green we've got the y-axis, and in blue there we've got the z-axis, that third dimension. So moving this around in 3 dimensions makes it a little bit easier for us to view. So we've got 3-dimensional axes here, and the cross product basically takes two vectors A and B and returns a vector that's perpendicular to both of them. That's what it does. That's what the cross product does. So that's quite an intuitive way of doing it, right? If you want to take two vectors and multiply them together to get a third vector, it might make sense for them to be perpendicular, that third vector. Because if it wasn't perpendicular, if I said A times B goes in this direction, somewhere in between them, for example, could do that. It goes in between them. That sort of product wouldn't make so much sense because A could be projected into its own multiplication, right? So A would have a part in its own multiplication that is not equal to its length. So imagine if I had A here and B here, and A cross B, which I've just invented, went exactly between them. Then A could project into A cross B, and that projection wouldn't be the size of A, it'd be some other weird thing. So that sort of invention, that sort of definition of the cross product doesn't make sense at all, because it gives us contradictory information about our vectors. Whereas if we make A cross B perpendicular to A and B, then the projection of A into A cross B is 0. In other words, its direction can't be projected into its multiplication. It's completely separate from it. In fact, the cross product forms a sort of coordinate system for us. So if X is in this direction, Y is in this direction, and Z is in this direction, they're all right angles to each other. If A is in this direction, B is in that direction, A cross B gives you something that's at a right angle to them both. It sort of gives you a coordinate system. A cross B, there's a right angle between them. A cross B and B, there's a right angle between those. So I'm just trying to conceptually get across what the cross product is right now. So A cross B, the cross product, not the dot product, gives a vector that is perpendicular to both A and B. And its length, well, this is the part that's like scalar multiplication. This is the part that is like the dot product. Its length is the modulus of A, the modulus of B, sine theta now. So A cross B is modulus of A, modulus of B, sine theta. So we're going to look at what that means in a little while. There it is. A cross B is mod A, mod B, sine theta, and then there's a bit of vector there. So what I just want us to do now is get a bit more of an intuitive understanding of it before we take it forwards. So what I can do is I can use these things up the side. This is the definition of vectors. This C point here effectively allows me to change the vector A. So if I make C 2 times as big, watch that vector A there. It got 2 times big. A cross B got 2 times as big. So if I take that away, shrunk down. Well, 2 times-ish. If I make it 3 times as big, it gets even bigger. And the same is true with B as well. So this point B is the vector B. So if I make that 2 times bigger, check out the vector B gets bigger. The cross product gets bigger as well. Gets bigger. And then it's back to normal. What happens then if I change the direction of A? So what if this doesn't just change in length, I change its direction? I'll change this value 3 to 4. So it changes its direction in the x direction. It'll drag it a little bit along in the x direction. If I do that, watch what happens to both A and A cross B. A goes a bit in the x direction, and A cross B also got dragged a bit towards the x direction. But it's still at a right angle to both A and B, and it always will be, because that's how the dot product works. So if I change this not to 4 but to like 8, oh, not 48, just to 8, there, it's got even bigger. So I'm making that vector A longer by dragging it along in the x direction. The result of that is it makes this cross product longer. I'm also changing the direction of A, and the result of that is it changes the direction of A cross B as well, but they're still at right angles to one another. So A cross B, what did this start for? It was 3. A cross B gives you a new vector that's perpendicular to both A and B, and it's related to the lengths of A and B, just like scalar multiplication. So we're going to get into bits of the interesting stuff, the mathematics behind this in a little while, but what I finally want to introduce you to is this thing at the back, this dashed arrow. Check this out. B cross A. So A cross B and B cross A. Let's think about normal multiplication. 3 times 5, 15. 5 times 3, 15. It's the same in both directions, right? Don't matter which way around I do it. Dot product A dot B and B dot A. We proved last lecture, last session, that they're also the same in both directions. So A dot B and B dot A are exactly the same vector. We can prove that. But what we're going to show in a minute is that if we define the cross product to be at a right angle to A and B, then if we do A cross B, we get this vector. If we do B cross A, we get exactly the opposite vector. Same length, but in exactly the opposite direction. So A cross B is minus B cross A. Oh, you've seen this hair bit here? Sticking up at the back. Okay, A cross B is equal to minus B cross A. So that's something that may be new. Something that you may never have seen before is that a multiplication operation, because we are basically timesing these things together in a sort of vector form, a multiplication operation is different when you reverse the components. So A cross B is minus B cross A, and we'll see why that is shortly. Okay, let's move on to the maths of this. Let's get rid of GeoGebra for now, and we'll move back to the PowerPoint thing. We'll keep the screenshot up though. So there's the screenshot. A cross B is there, B cross A is the dashed line at the back. There's A and there's B. Nice. If I have two vectors A and B and I want a vector output, then the most useful direction for that output is perpendicular to both of the input vectors. We've seen why that is. So we can define this using unit vectors, right? Using I, J, and K, we can define something that's completely general for all cross products. So for example, I can say I cross J, X direction cross Y direction equals the Z direction. That's useful, I think. That's called a right-handed coordinate system. Cartesian coordinates, right-handed coordinates. So X goes to the right, Y goes up, Z comes towards us in that case. So I cross J equals K. X cross Y direction equals Z direction. Unit vectors. So we're going to define that to be true. And then we can start rotating around then. So Y cross Z equals X, or J cross K equals I, and K cross I equals J. Right? So we can see I, J, K, I, J, K, I, J, K. It's kind of like a cycle. I, J, K, I, J, K, I, J, K. In each case, we don't pick up that minus sign, right? I cross K is J, I cross J is K, J cross K is I, K cross I is J. That makes sense for our unit vectors because each one of these is perpendicular to the others, and so our need for one vector cross the next vector to be perpendicular to them both works out well. But now let's reverse these things. J cross I then is minus k. K cross j is minus I, and I cross k is minus j. So that picks up our need for the cross product to be different or negative if we reverse those two input vectors around. We'll see why that's important shortly. But basically this is what we've got. This cycle. So the red cycle is on the left and the blue cycle is on the right. And we can see then that these unit vectors, which has hats on, like I said last lecture, unit vectors sometimes have hats. The red cycle, I cross j, gives us k, j cross k gives us I, k, I, j, other way around, I, and we're on the blue arrows now, so I cross k is minus j. Actually, we'll start here. J cross I minus k, I cross k minus j, k cross j minus I. So this cycle and these representations are exactly the same thing. So that's nice. That also would mean, if we follow the logic of these things through, that I cross I, j cross j, k cross k are going to equal 0. Because if I've got two vectors in the same direction, if you think about what that looks like in your mind, there are infinite ways that you could have a vector that's perpendicular to two vectors that are the same. Infinite ways. So the easiest way to define the cross product is by setting these things equal to 0. Right? To compensate for that infinite number of options to choose from, we set it equal to 0. That's how we define this. So you can see that unlike the cross product, unlike the dot product, which has a very intuitive understanding to it, the cross product is very much constructed. We construct these things because we need them to be this way in order to do calculations. And as we see what the actual formula for the cross product looks like, we'll see exactly why this is the case. But before we do that, all of these cycles can be brought down into something called the right-hand rule. So remember I mentioned that x, y, z is a right-handed coordinate system, as in you go from x to y anti-clockwise. You go y to z anti-clockwise, z to x anti-clockwise. That means it's a right-handed coordinate system. That's how we define it. The right-hand rule tells us how we can work out where the cross product will point. So here's the first one. If I put my hand like this, it looks daft, but it's got to be my right hand because it's a right-handed coordinate system. That's exactly why it looks like this. If I put my forefinger in the direction of A, the first vector, and my second finger in the direction of B, then my thumb will point in the direction of A cross B. So if that's X and that's Y, then my thumb is Z, right? So that's how we work out which direction the cross product of two vectors will point in. And I can bring my two fingers as close together as I want, right? It's still my thumb pointing perpendicular to both of them. And that's why this works, because we can form a right angle between our thumb and these vectors. And so we can put them in any orientation we want. And our thumb will point in the direction of A cross B. A, B, A cross B. That's how it works. A better one that I find a lot interesting, a lot more useful actually, because I always forget which way round my fingers are for this one, is the corkscrew rule. It's something similar. You use your hand, you flatten it out and you point your fingers in the direction of the first vector, curl your hand round into the direction of the second, and then your thumb points in the direction of the third. It's exactly the same as this, it's just a bit easier. Fingers in the direction of A, curl them round in the direction of B, and your thumb will again point in the direction of A cross B. So those are two ways of working out graphically using your own hand which way your new vector will point. And it's just a constructed thing. The cross product's a constructed thing, and this is just a way of understanding what it's doing. So we're back to the diagram here, right? A and B, and then there's A cross B. Some vital identities that you'll need for this. So whereas the Dot product was mod A, mod B, cos theta. The cross product is mod A, size of A, size of B, sine of the angle between them. And then a bit of unit vector now. So this unit vector is the unit vector that points in the direction of the cross product. So A cross B, it turns out, is the size of A, the size of B. So it has that property of it's related to both the size of A and B, just like normal multiplication. It's the sine of the angle between them this time. And then it's got a unit vector attached to it. So the output of this is a vector. And its magnitude is mod A, mod B, sine theta. And its direction is the direction defined by all the i's and j's adding together and stuff like that. So one thing you might think, if the dot product is cos theta, because it's intuitive, and we've constructed this one to be sine theta, then we might be able to square this, square the dot product, factor out A and B, sine squared plus cos squared equals 1. We can do trigonometric identities to compare and combine these vectors together. But don't worry about that for now. We've got this formula. It's similar to the dot product, but it's sine theta instead of cos theta, and it's got this unit vector attached. A cross B is minus B cross A because we've defined it to be that way. What is the cross product really? I've tried to describe it graphically, but the cross product between two vectors A and B gives a third vector, n hat, unit vector, in a direction parallel to both A and B. That vector is proportional to the magnitude of both A and B and is analogous to scalar multiplication. Actually, that's not n hat, it's just n. N hat's the unit vector bit. Give me a minute. Might as well change it here to not be confusing. Insert equation, accent, underline. There it is. N. There we go. So n hat's the unit vector. Cross product between A and B gives a third vector n, a full vector in a direction parallel to both A and B. That vector is proportional to the magnitude of A, the magnitude of B, analogous to scalar multiplication. It's also proportional to the sign between them, and it has a unit vector n hat. So that's what the cross product is. That's the definition of the cross product. As a column vector, we can calculate the cross product this way. So x1, y1, z1, x2, y2, z2. The cross product is y1, z2 minus y2, z1, x2, z1 minus... Complicated formula, but that is the cross product. Just like how we had an algebraic way of calculating the dot product with x1, x2 plus y1, y2 plus z1, z2. The cross product also has an algebraic form. It's a little bit more complicated. And we can actually prove that to ourselves using I cross I equals 0, I cross j equals k, j cross k equals I. If we times these things out, just like we would times out regular brackets, we would get x1i times x2i. Well, I cross I is 0, so that's going. x1i cross y2j, well, that's going to be x1 y2, I cross j is k, x1 y2 is in the z part, the k part. So if we multiply out these brackets using the rules of the cross product that we ourselves have defined, I cross j equals k, j cross k equals I, etc., we get this, which therefore can represent in a column form like this. Unlike all the other ones when I said, oh, just times it together, just add the components together, this one is a little bit more complicated. So we've constructed the dot product, the cross product, in order to give mod A, mod B, sine theta, and to give us a vector that's perpendicular to both the vectors, right? We've constructed it to be that way. But the reason that the algebra works out like this, and that this is exactly equal to this, is a little more complicated than the dot product one. You need matrices to do it. So I've said, but wait, why is it that A cross B equals this equals, why is that the same? Why is that the same? This is a very optional task. I'm not going to do it here because it's the maths of it. It requires matrix algebra to do it simply. If you don't have matrices, there are a couple of videos online that will try and explain it algebraically. It's very messy. So here's a video for that. For a more intuitive understanding of what the cross product is, a couple of videos here from an online maths teacher called 3 Blue 1 Brown. Absolute genius. I advertise all of his videos because they're amazing. He's got an animation software that's better than anything I can do, such that I even use it in some of my lectures because it's awesome. So have a look at his videos for a more intuitive understanding of what the cross product is. Have a look at this video to understand why this is true, given our rules of the cross product. But for now, and I really, really don't like doing this particularly, but you understand, I hope, the concepts behind the cross product. You understand that you get a vector and another vector, and your cross product is perpendicular to both of them. That's the concept behind it. Just imagine we've constructed it to be that way, and that because of our rules, the algebra just works out that way. Because of our rules that I cross I is equal to 0 and I cross j is equal to k, this algebraic form naturally comes out. And this algebraic form, I'm just going to need you to take my word for it for now, until you've done matrix algebra, and then it becomes a lot easier. But that brings us on, so that's everything to do with vector multiplication, right? We've done it by scalars. So if you times a vector by a scalar, it just increases its length. We've done the dot product, which is two vectors in and a scalar out. And we've done the cross product, which is two vectors in and a vector out, and that vector is perpendicular to both of them. So those are the three ways that we can multiply vectors together. And that gives us a complete way of describing basically any vector space. Any way we can describe vectors, we can do it with those operations. So that means we're done, except for division. Vector and scalar in, vector out. If I've got a column vector and I do x, y, z, and I divide it by c, it's just x divided by c, y divided by c, z divided by c. So vector division by a scalar is exactly the same as vector multiplication by a scalar, right? It's just the inverse operation, so it has all the same rules. The algebra form of that is xi plus y. Oh, there's another time. Typos all over the place here. That's z. And that's z. Right. X, y, z divided by c. So you just divide all the components by c as well. Easy peasy. And the diagram for that is if I've got a vector r here and I divide it by c, it just shortens it by that factor. So it's exactly the same as multiplication, right? I've even put 1 divided by c in front of that vector to show that if I times it by c, it would go longer. So it's exactly the same. Just divide each component by the scalar. So the interesting thing here is that while we can do multiplication by any means, we can times scalars together, we can times vectors together, we can times vectors and scalars, scalars and vectors. What would it mean to divide a scalar by a vector? That's the interesting thing here, I think. So we can multiply them all together, no problem. I can divide a scalar by a scalar. I can even divide a vector by a scalar. It's the same as timesing a vector by a scalar, right? But what would it mean to divide a scalar by a vector? If I've got something that just has size and no direction, how can I divide it by a direction? What does that even mean, to divide by a direction? You might think, okay, well, you get rid of the unit vector part. Okay, but no, it doesn't work like that. To divide a scalar, which doesn't even have a unit vector, right, by a vector makes no sense. So we can't divide a scalar by a vector. We can't do it. The operation makes no sense. Almost like dividing by 0. That operation makes no sense. It is an incorrect way of viewing what these things are. Equally, if I can not divide a scale by a vector, might think I can divide a vector by a vector, because a vector's got a unit vector and a size, and a vector's got a unit vector and a size, so can we divide the unit vector away? Maybe, but we've got two forms of vector multiplication, right? We've got the dot product, which takes two vectors and produces a scalar. So if anything, we would want to take a scalar, divide it by a vector, and somehow get another vector back if we're living with the dot product. Vector divided by a vector, you might think, okay, the cross product gives us a vector and a vector times together. So can we use the inverse of the cross product to divide a vector by a vector? Not really. It doesn't work like that. You can't just like chop up a vector and see how many parts are in it, which is what scalar division is, right? Because the cross product defines a vector in a perpendicular direction. So actually, none of A and B are inside A cross B because it's in a completely different direction. So dividing a vector by a vector in terms of the cross product makes no sense at all. So we can't divide a vector by a vector. That operation also makes no sense. So with vector division, really all we can do is vectors divided by scalars and scalars divided by scalars. Scalars are the easy ones, it turns out. So that brings us on to, let's say, a not optional task, right? We're going to do some calculations with vectors now to bring all this stuff we've done together. So we've got two vectors, A and B. What I want you to do is calculate and represent using a diagram. And I've put your preferred written format. I would use algebra if I was you, but you can use column vectors if you really want. Explicitly calculate and represent using both a diagram and your preferred written format, A plus B. So we've seen a diagram for that. A minus B, that's going to be an important one for electromagnetism. So really concentrate on what A minus B is. Draw it on a diagram. A dot B, B dot A, and cos theta. So they're not vectors, so you can't really write them on a diagram, but calculate them. Calculate these angles. A cross B, B cross A, you can do on a diagram, so put those on a diagram. Sine theta and n hat, the unit vector corresponding to A cross B and B cross A. They'll take some creative thinking, but you've already got everything you need. So remember before when I said there might be some links between dot products and cross products because of the sine and the cos? Think about that. I'm going to ask you the question then, why is the dot product between these two things relatively small? So I'm giving you a clue, it's relatively small. Whereas the magnitude of the cross product is relatively big. Hint, think about the angles. And then we've got another question. So a smart device is anonymously tracking movement. Every day it measures that its owner first moves from position R1 to R2 at a slow walking speed, R2 to R3 at a driving speed, and then finally from R3 to R4. Each segment is approximately a straight line. What is the total distance travelled by the owner of the smart device? What is the total displacement of the owner of the smart device? And from these physical measurements, data that companies collect about us every day using our phones, using our location data, using interactions between our phones and ticket machines on public transport, shops we go in, things like this. What information can we infer about the owner of the smart device just from these physical measurements? So this question's a bit more societal, but it's important because it uses physics. This one, for the two vectors r equals 1, 2, 3 and f equals 5j plus 3k, calculate f dot r, the dot product between f and r. And for these two vectors, the cross product between r and f. Think about the direction there. The order of these two things is going to be important. So that's your questions. You can skip back in the video to get them on screen. That should take you something like an hour, I think. So take an hour to do those questions. Pause the video, and when you've had enough, Unpause the video and I'll go through the solutions. Right, let's do some solutions. So two vectors, A is equal to 3i plus 4j plus k, and B is equal to 4i minus 3j plus k. We can do this. I've probably just done the algebra. Yeah, I've just done the algebra. I haven't done the diagram, sorry. But A plus B, you add the I bits together, you add the j bits together, and you add the k bits together. 7i plus j plus 2k, no problem. A minus B, minus the i's, minus the j's, minus the k's. 3 minus 4 is minus 1, 4 minus 3 is plus 7, and k, 1 minus 1k is 0. So the k bit has gone entirely. Interesting. A dot B, that's equal to B dot A. And that's equal to 1. That's nice. So 3 times 4 plus 4 times minus 3, so that's 0. So the I and j components cancel, leaving only the k components. 1 times 1 is equal to 1. And so the cos of the angle then, A dot B is mod A mod B cos theta, so I can just divide A dot B by mod A, and mod B gives me cos theta, which is 1 divided by 26. I've got a calculator somewhere. Here we go. Let's see what the actual angle is. Cos inverse of 1 divided by 26. 87.80 degrees. That's pretty close to a right angle. I wonder if that's going to be important in the next couple of questions. A cross B, bit harder, but we're using the rules given to us before. So I cross I is 0, I cross j is k, j cross k is I, those rules. So we've got I, let's get the I components first. So the I components are going to be j cross k is 4 lots of I, and k cross j is minus 3 lots of minus I. So that's 3 lots of I, 4 lots of I, 7 lots of I. Same with j. Here's the interesting bit. If we cross product these things together, we get minus 25 lots of k. So all of a sudden we've got 3s, 4s, these are kind of small numbers, 7's alright, 25k. So all of a sudden the cross product between these two things is massive. The dot product, on the other hand, quite small, 1. That's interesting, I think. And so the unit vector then of this. If a vector is its size multiplied by its direction, its magnitude multiplied by its direction, then the unit vector is simply the cross product vector divided by the magnitude of the cross product vector, just like any unit vector. And so if we calculate the magnitude of this, it's 7 squared plus 1 squared plus 25 squared square rooted, gives us this answer. I've done it in surd form because I wanted to make a point about sines and coses here. But in general, 7 divided by 15 root 3, just give it to 3 decimal places. In physics, these things represent physical quantities, not exact mathematical things. So 3 decimal places. 3 sig figs or 2 decimal places would be good. But here I've left them exactly this way. And so now we can work out sine theta, right? Because the magnitude of the cross product is equal to mod A mod B sine theta. So the magnitude divided by mod A and mod B is 15 root 3 divided by 26. Interesting that there's a 26 here and a 26 here. Same angle, right? Sine squared plus cos squared. Turns out it equals 1. We can do, I did it this way for some reason, right? Cos squared is square root of 1 minus sine squared. 1 minus that squared is 225 times, I can't do that in my head. If I had a calculator though, it'd give me 1 over 26, which is exactly what we got here. So that means that the cross product does indeed give us sine theta. And it's related to the dot product via that angle. Super interesting. I wonder, is this making us think? Trigonometry's got like all these weird things like sines and coses coming all over the place, but now we've got the dot product and the cross product. We can do trigonometry using multiplications. We can do it using vectors. We can do it using standard algebraic tools without getting trigonometry as involved, which is quite interesting. For those of you who've done further maths, you'll know what I'm going to say maybe, but for those of you who haven't, there's this thing called complex numbers, which actually combines the ideas of vectors and trigonometry together into a beautiful mathematical form where it makes working with waves a lot easier. So when you do complex numbers, you'll learn de Moivre's theorem, super important. You'll learn Euler's theorem and Euler's identity, which might be the most beautiful mathematical thing ever created in all of history. And it's really important. It's to do with vectors. So keep vectors in mind when you do those things, complex numbers. But for now, let's think about it. Why is the dot product relatively small, whereas the cross product magnitude is relatively big? I've put a hint, think about the angles between the vectors. Well, we worked out that the angle between those vectors is almost a right angle, right? Because the dot product has a cos theta in it, the closer that angle gets to a right angle, the closer cos theta gets to 0. So the dot product is 0 when things are at right angles. The cross product, on the other hand, has its maximum value when those things are at right angles. Its maximum value. On the other hand, if I'd chosen this question to have a very small angle, then the dot product would have been massive and the cross product would have been really small. Because cos theta, when it's close to 0, cos theta is 1, it's at its biggest. When sine theta, when the angle's close to 0, it's big. It's small even. So when things are at right angles, the cross product is massive, and when things are in the same direction, the dot product is massive. So the dot product and the cross product serve as markers to tell us whether or not two things are roughly in the same direction. Interesting. Very interesting. That's going to be quite useful when we're analysing trajectories of things and other physical things. Oh, hang on. I had another bit there. No. Angles between vectors. Can't have been important. Oh, yeah. So, I've just remembered. So, the cross product, you've probably not used it before, but you've used a simplified version of it before. If you ever learned at A level or at GCSE about magnetism, and you learned that the force because of a magnet on a charge that's moving with a speed, force equals BQV, or magnetic field, times by the charge times by the speed of that charge. You'll have noticed perhaps in every single question it said that the magnetic field is at a right angle to the direction of motion of the particle, right? That's because, and you'll learn about this in second year physics, maybe even first year physics actually, that the actual formula for the magnetic force on a moving charge is Q, the charge, V cross B, where V is the velocity vector and B is the magnetic field vector. So it's F equals Q, V cross B. So it's a cross product. Those things have to be at right angles to one another. And it turns out that a lot of the case with magnetic fields, things have to be at right angles, whereas with electric fields, things have to be in the same direction. So electric fields and magnetic fields are comparable in a similar way physically as the dot product and the cross product are mathematically. And that's some really interesting first and second year physics stuff right there. Really interesting. But let's move on to this next question. A smart device is anonymously tracking movement. It's not anonymous at all. It can work out who you are given what path you take every day. So even if your name's not attached to it, it knows exactly who you are. But anyway, Big Brother aside, every day it measures that its owner first moves from position R1, 0, 0, the origin, to R2 at slow walking speed, R2 to R3 at driving speed, and R3 to R4. Each segment is approximately a straight line. What is the total distance travelled by the owner of this smart device, right? The total distance travelled is every single segment's length added together, right? Every single segment's length added together. How do we get each segment? If I want to know from R1 to R2 what is the vector between them, here it is, R2 minus R1. So here again we see why taking vectors away from each other is really important, because the vector from one position to another is the final vector minus the initial vector. Exactly like scalars, right? From one to the other is the last one minus the previous one. And so the distance is the magnitude of the first segment plus the magnitude of the second segment plus the magnitude of the third segment, all of them added together. So I've square rooted and added square root. There we go. 6.70 kilometers. Nice. What is the total displacement of the owner of the smart device? So displacement is not distance. Displacement is the vector from the initial position to the final position. Not the path. Not the exact complete path, but just the vector from the start to the end. That's what displacement is. So therefore, the displacement vector is just the final one minus the initial one, which is easy done, because it started at 0, 0, so it's just R4, basically. The magnitude of that is 6.42 kilometers. The magnitude of this was 6.7 kilometers, right? So that means that the displacement is roughly equivalent. It's very, very, very close to the total path length, which tells us that that path is relatively straight, doesn't it? Because if our total displacement vector is roughly equal to the total length, then our path can't be deviating from that displacement vector very much. So that's a bit of physical intuition there to do with vectors. I've written a little bit about this because it's important what it means, right? From these physical measurements, what information can I infer? I asked this question just to show the power of even basic physics in the modern world and the responsibility we have as physicists. So before we've even moved away from vectors, I'm telling you about the responsibility we have as physicists in the modern world. Really important stuff. We'll start learning stuff in mechanics, specifically in semester 1, that have real ethical implications to them. So it's important that we think about the ethics right now, because from these calculations I can infer the owner of this smart device probably takes the bus to work or university, right? Because they walk a little bit to start with, but it's 100 metres. No one's car's parked 100 metres away from their house, but bus stops are 100 metres away from people's houses. People choose where they live based on where bus stops are. So R1 to R2, I might infer, is the distance to the local bus stop, right? And then they go at a driving speed about 5 kilometres, probably going to work, and then there's a little bit of extra on top as they walk from parking to work, right? Or university, whatever. Small distance at the start and at the end, suggesting no car. Because that little distance here is bigger than the distance to most people's car park. Further, because the total distance travelled and total displacement magnitude are similar, I can also infer the journey is pretty much a straight line, and thus alternative forms of transport will not speed up the journey. So this person can't have their journey speeded up by alternative forms of transport. So if I was an advertiser, I would target them probably with faster vehicles rather than things that take alternative routes, if they were interested in speed or something. If it turns out that they were interested in green stuff as well, I might advertise them green cars and bicycles. But the point I'm making is, I'm not an advertiser. I wouldn't do this. I find it quite unethical. But from this data, I can do this. And all I've done here is used very, very basic vectors and a bit of physical intuition. And all of a sudden I can start advertising and selling things to people. So physics gives you this ability to apply maths to the real world and make really, really important inferences about things beyond just how things move. And this is the sort of stuff that we need to think about, as well as just doing physics because it's interesting. So keep that in mind. But now onto these things, let's do it. For the two vectors r and f, calculate f dot r, right? So we've got 1 times nothing, because there is no I component. 2 times 5 plus 3 times 3, 19 Newton meters. F dot r is 19 Newton meters. For the two vectors r and f, calculate r cross f. It turns out that r cross f is 13k Newton meters. So this one's a vector. This one is a scalar. R cross f, 13k Newton meters. F dot r, 19 Newton meters. Super important. They've got the same units, but they're very, very different quantities. Right? This one's a scalar, this one's a vector, this one has a direction, this one doesn't. So even though they've got the same units, actually units of energy, they're very, very different quantities. So don't underestimate what it means to be a vector and a scalar. These are not the same thing at all, just because they've got the same units. Nor can you add them together because they've got units that are the same. Direction, super important. That's what we're going to get from this. So here's the congratulations bit. If you've done these questions correctly, you've just calculated some quite hard vector maths, right? It's hard stuff. For the first time, doing all these weird operations is hard. Very real application of vectors in physics to make models and predictions, right, of how people get to work. The work done by a constant force F on a particle moving along the vector R. So that's what that dot product was there. The work done by a constant force F on a particle moving along that vector, along that path. The work done is F dot R. There we go. That's the work done. A form of physics calculation of energy. The torque about the z-axis due to a force F applied to a particle at position R. So that last question we did, where the answer was 13k Newton meters, we've just calculated the torque. And because the answer gave us the vector k, the unit vector k, that means that the torque is rotating, the object is rotating around the z-axis. So just by I just gave you some maths problems, right? That was purely maths, right? I didn't mention anything to do with the physics underneath it, none at all. But you've just calculated the work done by a constant force on a particle and the torque due to a force on a particle. So if you ever struggle bringing maths and physics together, which is sometimes the case for first-year physicists, bringing those maths and physics ideas together to unify them, to realise that the maths you're doing applies to that real physical world out there. If you ever struggle bringing those conceptual ideas together, just remember you've done it already. You've just done it right now. You've already done it. So when you add that physical intuition on top, don't worry about it, because underneath it all, it's just maths. Last thing before we close out for this session, some resources. So 3 Blue 1 Brown, that guy I mentioned before, he's got a series on linear algebra, or in other words, how to do matrices and vectors, right? If you are interested in just the pure maths of how this sort of stuff works, I strongly advise you go and watch his entire series on linear algebra. It's absolutely mind-blowing. I learned matrices at school, and all I learned was the weird formulas for multiplying them together, weird formulas for calculating the determinant. But what I never learned was why. Why do these things exist? Why do we have a square of numbers, right? What's the point? This series explains exactly why, and it's so well described that I think it's wonderful. I think you should watch it. Goes a bit further than we need to right now. You'll probably need it either in next year or the year after. Especially in quantum mechanics and quantum field theory if you take it that far. So that's what I suggest you watch that lecture for. And GeoGebra, that's the tool I was using to draw maths and stuff. I use it to draw vectors. Super useful. I'll put some install instructions on Minerva for the people who are at University of Leeds. Here's the download thing. You can download a desktop version. So that's it for vectors. That's the first 2 sessions. I'm going to do one more. I'm probably going to film it this evening. And that's going to be on calculus. And once we've got vectors down, the mathematics behind it and a bit of physical intuition, and we've got calculus down, a bit of mathematics and the physical intuition, we're ready to go for the entire first year course. Right, the entire thing, we're ready to go. So, thanks for watching. Come by for the 3rd one, and then I'll see you in mechanics lectures.